this talk basically concerns classification schemes tectonicists are using in studying origins. I mean, personally, I always felt that the topic I'm going to talk about is rather trivial, but working all over the world in different types of origins, I noticed that there's a lot of confusion between geologists about what is accretion and what is collision of terrains and the various different types of collisions. So I will give you my ideas about it. And the problem is that a lot of these terms are qualitative rather than quantitative. So the scheme you see here, this is a division of origins on basis of temperature. And this is a more quantitative approach by metamorphic petrologists, whether origins are hot or cold. At least you can calculate in which field you are. And on the left side, you see an example of a hot origin in eastern Brazil, where you see clinopyroxene and amphibolites, which are melted in situ, forming trontiumite tonallitic melts, and then with temperatures in the order of about 800 degrees Celsius. So, because origins have been divided into accretionary and collisional origins, there's a lot of geologists who think that accretion is a different process than collisional. And I will argue that there is basically no difference between an accretion of a terrain or collision. The two terms basically mean the same. But when it's used on an orogenic scale, there appears to be some kind of difference. But we'll show is that it all depends on the person who defines what he means with a collisional origins and what he means with an accretionary origins. So here we're looking at the Southwest Pacific, and we see an accretionary origin in progress. Australia is moving to the north with a speed of about 7 to 8 centimeters a year, and is colliding with all the arcs and oceanic plateaus and ribbon continents, etc., which are themselves also colliding with each other. And you could imagine that in the future, all these terrains are basically going to be smeared out along the Southeast Asian margin. What you also see is that Australia in the western part is on the verge of colliding with Sundaland, which forms part of Eurasia. So basically the start of a continent-continent collision. But as you can see, the collision will not be finished soon because there's still lots of oceanic lithosphere to its west. And so this origin will become an accretionary origin, but it also involves all kinds of continental material. So the problem is where to draw the line. So the accretionary origin where I am most familiar with is the Northern Appalachians and the Caledonites in Europe. And this origin started out as an accretionary origins where Laurentia was basically growing by addition of all kinds of material coming from, in present coordinates, from the east. And then eventually at the end, Gondwana arrived and we formed the supercontinent Pangaea. And then the accretionary origin became a collisional origin, if you use this kind of terminology. And as what we will show you is that most collisional origins have an accretionary orogenic stage prior to a collisional origin. Another problem is there's a lot of these terrains that accreted to Laurentia prior to the final collision between Gondwana and Laurussia. Is a lot of these terrains are continental. They're little ribbon-sized continental terrains. And hence, what is the difference between a ribbon continent and a larger continent? So where do you draw the line? This is how you can form accretionary origins. If you go to the one on the left, we see an imaginary continent with a ribbon in front of it, and there's an arc approaching. Subduction is going underneath the arc. The buoyant ribbon collides with the arc, And since the ribbon, of course, it has a finite length, and the ocean on both sides is still subducting, eventually the subduction will step back behind the ribbon until that the combined arc and ribbon collide with the continent. And then if that happens, then eventually a new subduction zone may form outboard by a subduction polarity reversal. And I will show you some examples where that has happened in recent history. So this is generally the process what you're seeing happening in accretionary origins. And on the right, you can see some examples from the Appalachians where you see the Gondwana-derived Ganderia, which is colliding with Laurentia, and then subduction steps back outboard and brings in Avalonia, forming the Salinic and Akkadian orogenies, respectively. Now let's go to India, which is the type example of a collisional origin. If you look on the west side and on the east side, you still see that there's subduction going on of oceanic lithosphere. So there's no continental collision taking place there. India is, because it's still sitting on the Indian plate, is still converging with Eurasia. Of course, it is very buoyant. There's a large continental mass, doesn't really want to go down. And as a result, the oceanic crust to the south of India is at the moment buckling, large wavelength faults, and there's lithosphere penetrating reverse faults forming right there. And some people argue that there is a new plate boundary forming to the south of India. And if that takes place, then you could argue that there maybe in the future, there will be a new subduction zone forming to the south of India. And if that happens, that may join up with the subduction zone that's now taking place beneath Sumatra and the one to the Macron to its northwest. And so that, and if that takes place, then there may be a whole new subduction zone basically zipping open along the west coast of India. And if you look at India itself, then you will see that it is not a very simple continent-continent collision, because India collided first, and this is a slide from Jean-Pierre Burck, first with the Kohistan-Ladakh Arc, and then the composite India collided then with Eurasia. So even if you call this a collisional origin, there was an earlier accretionary stage. So in my opinion, there is no difference between accretion and collision of terrains. And the difference between an accretionary and collisional origin is mainly one of scale. And it is very qualitative. Another term that is used by many workers, especially in Europe and in Asia, is hard and soft collisions. They are not an invention of me. I was first introduced to these terms when I went to Oxford for a sabbatical, and John Dewey was using this term left, right, and center. And he never really explained to me what he meant with hard and soft, but it was clear that it had something to do with the scale of the deformation damage, analogous to a car colliding with the car next to it when he's parking, and you get a little bumper damage, or you're driving your car into a tree and the whole car is deformed. So the latter one is a hard collision, and the bumper collision is a soft one. And as I will try to show you or argue, is that soft collisions are mainly restricted to short-lived accretionary events such as arc-arc or arc-continent collisions. And then they're basically and these are followed then with step backs or polarity reversals. And then basically the stress is transferred to another zone and then leaving this place alone. So here we go into the Southwest Pacific and the eastern part of the Indian Ocean. There are 3 collisions in progress right now in this area. There is the Luzon Arc in Taiwan that's colliding with China. This collision has already taken place in the north of Taiwan about 6-7 million years ago. And this collision is propagating to the south and will take place in about 10 to 50 million years at the latitude of the Philippines. So it's a highly diagonous collision. The same is happening in Australia, the collision between the Banda Arc and in Australia. The collision has taken place at the longitude of Timor. and Banda, and it's propagating both to the west and to the east, as indicated by those arrows. And at this moment, Australia is just basically colliding with the Sunda Arc, which is underlain by Eurasian crust. And then there's another collision here between Australia in Papua New Guinea and the Bismarck Arc, and that collision is propagating towards the east. And so as you see, all these collisions are coeval. They are very localized. They involve arc continent collisions. And the one in between Australia and the Banda and Sunda Arc is basically a continent-continent collision, but that will still continue for a long time to come because there's still lots of oceanic lithosphere preserved. And as you can see, to the north of Banda, there is now thrusting towards the south. So you could argue that there is a subduction polarity reversal in process right there. So this is just a simplified diagram of a generic arc continent collision, and which starts out as soft. So the collision basically starts is when the leading edge of the continental crust is entering the trench. At that stage, the trench, the 4-deep trench, basically becomes a foreland basin. And if you have good fossil control and you know exactly where the sediments are coming from, then you can estimate approximately when this collision basically starts. And I will give you an example of that in the next couple of slides. But also what you will see is that the deformation is mainly localized in the lower plate that is progressively basically entering the trench. And the rocks of the lower plate are going to be incorporated in the overlying, this time, the collisional orogenic wedge. And so deformation is mainly localized in the lower plate. And this may be the key to basically separating hard and soft collisions. So this is a really good paper, which I really liked. This is a very detailed paper based on very detailed seismic and exploration wells looking for oil and gas in the Timor Sea between Timor and Australia. And this is from Sakwap et al. 2017 in Tectonic Physics. And you can see 6-7 million years ago, the leading edge of Australia entered the trench. And then over the last 6-7 million years, progressively more Australian material entered the trench. And as you can see there on the lower figure, the collisional wedge is basically made up of Australian sediments incorporated into it. And most of Timor is actually Australian material. On top of it, we have a 4-arc slab that is deformed to some extent, but the arc, the Banda Arc, further to the north is basically undeformed, certainly not penetratively. This is another example here of the Bismarck collision with Australia in Papua New Guinea. We originally had a collision to the north between Onton-Java Oceanic Plateau. It was too buoyant to go down, and it basically drove to set up another subduction to the south, which is now north dipping. So here we had a polarity reversal. And as you can see, this north dipping subduction zone goes all the way to the south, where now the northern tip of the Lord Howe Rise is entering the subduction zone. That island there is New Caledonia. And there's a bit of a very diffuse transfer zone between the Tonga Arc subduction zone and the Solomon Arc subduction zone, which is basically explained here on the right side of the figure. So this is a good example of polarity reversals taking place in the recent geological history. Now, I had the fortune to go with Alex, my co-author on this talk, to visit Taiwan, and we had a very good field trip to the Arc Continent collision, which is in progress. So the Arc Continent collision is over in the north. There's a polarity reversal that took place in that part of the world, and the Okinawa Trough, which is basically a back arc basin, has now migrated into Taiwan. And if you look at the topography of Taiwan, that is amazing contrast. In the north, it is almost at sea level. And in the middle, where the collision is in progress, and that is basically what you're seeing in figure B, you go from basically sea level to 3 kilometer height. And in the south, which is basically figure A, where the collision is just starting, it's just hardly any deformation to start with. And the person there who is with the microphone giving a lecture is John Suppy, and the person opposite to him is Dennis Brown, who were leading this IGCP field trip in Taiwan. And we're looking at the in the far distance, we're looking to the Lychee melange, which is at the suture between the Luzon Arc and the basically subducted Chinese margin, which is basically to our left. Now, if you look at the Luzon Arc, which is beyond the Lychee melange, that is basically undeformed. The arc is basically as pristine as you can see it. All the deformation is basically localized in the sediments of the Chinese margin. And on the top, you see a photo of the melange, and here's the Chinese investigator who is basically telling us all about it. And even more surprising is that the melange is not even lithified. When it started to rain, the matrix of the melange started to basically erode away, and it's progressively brought more blocks to the surface. This is basically the nature of the suture between the Luzon Arc and China in Taiwan. So another arc continent collision I visited was in 1997. I was invited by Mike Searle to come and visit him and work with him in Oman, where we were looking at the abduction of the Smile ophiolite. And the Smile ophiolite is basically an infant arc, already recognized by Julian Pierce in the 80s, and he called it the LaSalle arc. And this is another, what I would call a soft collision. And if you look at the interface between the abducted ophiolite and the underlying Oman margin, you will see that virtually all deformation is localized in the Arabian margin. And at the interface between the two, we have a huge serpentinite melange with lots of blocks plucked up from the lower plate, and as well as mafic dikes that are feeding basalts higher up, which are all broken up. But if you go into the ophiolite itself, the superstructure of it, it is very pristine compared to what is in the lower plate. And again, as you can see on the left top, you see it's a complex origin with subductions going on the several progress. And once this whole process is finished, there will be another accretionary origin ending in a collisional origin. So here, another example in the Urals, and compare it to Taiwan. And in both cases, you will see is that the deformation, the penetrated deformation and metamorphism is typically localized in the lower plate. But in both cases, also the forearc is strongly deformed and partly subducted in both cases, both in the Urals and in Taiwan. But the arc basically remains untouched. And the Magnitokorsk arc in the Urals and the Luzon arc in Taiwan. And so if you want to use terms soft versus hard, and I will argue that it may be useful in times, then maybe the state of deformation, the amount of shortening and penetrated deformation in the arc may be the key to how to distinguish them. If you do that, then there is a problem potentially, because compressive arcs, and as you can see here on this slide from Wouter Schellart in the 2004 paper in Nature, compressive arcs are relatively rare. They're indicated in red, And they are in the Central America, where I also worked, and in Japan, but most arcs are either extensional or they are neutral. Now, compressive arcs, they approach the trench faster than the trench rolls back. They're basically overriding their own trench, and hence the arc is compressive and will be deformed. So if you incorporate an compressive arcs in an origin later on, then it may be hard to separate a hard versus soft collision in that case without having very good time control and when and how it happened. Another thing, as you could look, these factors given in dark is basically the amount of slab rollback. And as you can see, the Tonga arc especially is rolling back with a speed of about 15 centimeters a year towards the east. And it is definitely a process that you should keep into mind. And this is another very interesting figure on the left. This is another from Wouter Schellart. It's in Journal of Geophysical Research, where he did a scaled experiment. The mantle here is is done here as a kind of a syrup, and with a stiff plate going down. And on the right, there's an experiment which a friend of mine, Claudio Vacena, showed me in his lab. And there's some interesting things going out of it. So the experiment of Wouter Schellart is two different types. One of them is a fixed trailing margin. And you could imagine that that is what's happening in the Mediterranean today. In the Mediterranean, Africa has collided with Europe on the western side. And on the eastern side, through Arabia, it has also collided with Europe, but there's a lot of Mediterranean oceanic lithosphere preserved in between. And the only way for that to basically keep subducting is with a fixed margin, which is not moving. And so basically the ocean is basically subducting by rolling back continuously, which is showed on the left-hand side. And as you can see, the slab steepens over time till it hits the bottom of the tank, and that is supposed to be the 650 discontinuity, which is difficult to penetrate by slabs, and that becomes a kind of a subduction graveyard. And then you can see then basically the slab flattens out on the left and eventually stabilizes until the all oceanic lithosphere is subducted. And you could imagine, because there is no driving mechanism to basically under-thrust the trailing margin underneath the continent that sits to the north of it, in this case Europe, and that there will be not much mechanism or not much force to drive this thing underneath it. So this could lead to some kind of relatively soft collision. On the other side, we have basically a margin that is not fixed and that can move. So you could imagine any continent that is moving and is basically moving, driven by the downgoing slab, and it behaves in a very similar way as the one on the left until the slab hits the 650 discontinuity, and then the slab starts to fold. And you can see that in some of the tomographic studies, like those presented by Karen Sicklock in underneath, which is now preserved underneath America, which of a subduction zone which is dipping towards the west, outboard of the Americas, and then eventually flattens out as well. And a really nice example of a hard collision is the Alps. This is from a very good paper, which I really recommend anybody to have a look at, by Escher and Chris Beaumont in Journal of Structural Geology in 1997. And here, the two combined, having a really good control on the geometry of the Alps and the understanding of the kinematic processes with the modeling skills of Chris Beaumont, and where they really show how this origin developed. And as you can see here, the Alps, if you want, you could argue that it had a original and accretionary stage, because there are two oceanic basins, the Valais Basin to the north and the Piemontese Basin to the south, which are separating a microcontinent, the Briançonnais, from Europe, as well as the Adrian Plate. And eventually, when the two oceanic basins closed, there became a hard collision. There is some kind of decoupling between the upper and lower crust, and the lower crust is subducting underneath Adria, and the upper plate, the Adrian plate, is highly deformed and metamorphosed and incorporated in big naps, which are now sitting at the highest structural level. So if you want, you could call this a hard collision, because the upper plate, although there's no arc, is highly involved in the origin. Very different from what you're seeing in the arc continent collisions. Now, what controls that? Now, this is another very interesting paper by Vogt and co-workers. This is the Dutch school in Utrecht and Amsterdam, who did the thermomechanical models, just like Beaumont makes them here in Canada. And so they argue is that the geometry of an origin is strongly dependent on the crustal rheology, where there's a weak zone between the upper and lower crust, the rate of convergence, and the initial temperature distribution. And I looked at that just to see if there's any indication what could control a collision to be soft versus hard. So when there's a weak coupling between the upper and the lower crust, an origin forms with a relatively low topography, and examples are the Carpathians in Eastern Europe and the Apennines in Italy. And as you can see, the deformation is mainly concentrated in the downgoing plate. The upper plate basically remains relatively untouched in this process, and there is a chance that the downgoing plate can reach deep levels and forming eclogite. And here you see two different, where one of them is coupled and the other one is not coupled, and with different convergence rates. So the one to the left is a coupled origin, and you can see that progressively the upper plate is becoming incorporated in the origin, forming back thrust rate of Sariage, whereas the decoupled upper-lower crust origins, basically it's a fallen propagating deformation, and that is mainly localized in rocks of the downgoing plate. So that would be approximating what you would see in a soft collision. So in strongly coupled crust, crustal shortening is accommodated by lithospheric mantle subduction, high topography, like you see in the Himalayas, elevated temperatures, doubly virgin origins, and involves the upper plate. And there could be deep exhumation in the hinterland if the climate conditions are correct and suitable for it. And fast convergence basically widens the origin. Now, is it all useful, these classification schemes? Sometimes it could be, and I will give you an example of this. And we go to Newfoundland, where I've worked extensively since 1990. So the area with all the colors in it, that is called the Dashwood zone in Newfoundland, and it is underlain by rocks of the Notre Dame Arc. And the two colors you have to look out for is the deep red and the pink colors, because these are the Ordovician arc plutons ranging from 490 to 477. And then there's the pink ones is arc and non-arc plutons, and they range from 469 to 457. Within this belt, there's a whole trail of material, of oceanic material, called the Luscious Bight Oceanic Tract, which is consisting of bonanitic rocks, island arc toliites, gabbros, and some ultramafic mantle material, which forms basically the basement into which these plutons intruded. On the western side of this belt, there in purple is what I call the Bayford Oceanic Tract, which are younger. The Luscious Bight Oceanic Tract is Cambrian, ranging from 510 to 500 million years old. The Bayford Oceanic Tract is late Cambrian, and most of the ophelites are around 490 to 489 million years old, which separates it from the Laurentian margin. In most western part of Newfoundland, you see the Bay of Islands ophiolite and the coastal complex. And what I will try to argue to you is that the style of deformation between the arc rocks and associated ophiolites to the east is very, very different to the Bay of Islands. Bay of Islands is basically a big slab of oceanic superconducting zone material that shows little deformation, certainly not penetrated deformation and metamorphism, whereas the rocks on the east side of the Cabot Fault are all deformed and metamorphosed. And there's also a difference in the timing of collision with the Laurentian margin, which is preserved in Bay Verde, which is moving with the Dashwood block. And I will show you that in a second. So if we go and look at the ophiolites along the Laurentian margin, the Ordovician ophiolites, they go from Quebec to Newfoundland. And this is these slides are from Alain Tremblay and Nicolas Pinet. And you can see is that the deformation is basically all localized in the downgoing plate, the Laurentian margin that was under thrust beneath the superconducting zone oceanic material. So that would be a typical soft collision, both in Newfoundland and in Quebec. However, if we look at the Notre Dame Arc, and I give you some samples here, it's a very different picture. The slide on in the top on the right is a tuff, which is interlayered with pillow basalts. And we dated the tuff, and it has an age of 489 plus minus 3 million years, done by Vicky McNichol at the GSC. And the basalts are relatively juvenile and basically forming part of the luscious bight oceanic tracts and arcs built on top of it. The interesting part of it, though, is that both the basalts and the felsic tuff were buried to great depths. The tuff here consists of jadarite, garnet, and sillimanite, and was metamorphosed to conditions around 750 and about 7-8 kilobars. And that work was done by Sally Pearson, one of my colleagues at the GSC. You can also see is that the rocks were polyphase deformed. You can see an early foliation that's folded by F2, and then they get refolded by F3 and F4. But that's not really a significant to the story. The important part here is that the upper plate rocks, in the form of these mafic and felsic volcanic rocks, were heavily deformed and buried. You can hear on the left side, we see the plutonic equivalents of those volcanics. We see tonalites here, which have an age of 483 plus minus 1 million years. They highly deformed and metamorphosed, and they get intruded by middle Ordovician tonalites and quartz diorites, which are undeformed at 462, and that suite ranges from about 467 to 459, and they're coming in during the deformation. Some plutons cut the deformation and are deformed, and others cut those as well. So it's basically a syntectonic syncollisional suite. And that also consistent with the age of the monacites and metamorphic zircon rims, which all give us ages in the range of about 465 to 459. So the arc is strongly penetratively deformed, and the rocks are buried to quite big depth. Now we go to Bay Verde, where I worked from 2006 to 2009 with my colleagues at the GSC, Sebastian Castangay, Tom Skulski, and Vicky McNichol. And you see, although the rocks are lower grade than they are to the south, the intensity of deformation and metamorphism is very similar. If you, in the top, you see a map of the Bay Verde margin, and you see the Point Rousse ophiolitic complex, and you see a photo below given. And here you see a bunch of Silurian trust, which are bringing the infrastructure of the ophiolite, the gabbros, and the ultramafic rocks above the basalts along the Deer Cove thrust system. The thrust is going to the southeast, but it is a retrograde feature overprinting an earlier metamorphism and an earlier deformation. If you can see the thrust zone here, the vein is a very good shear strength indicator. If you assume that the vein, like most veins do, open at a high angle to the extension direction, so approximately in this orientation, and then move through the shortening direction, like about this, and then now it's in the extensional field, and you can see that along this limb, the vein is Boudinized. There's all little blobs of the vein going all the way to there. So now it's in the extensional field. So if you resolve this, then you can see that the infinitesimal strain axis would resolve into basically a reverse sense of motion along the thrust. And if you look at the metamorphism, and I sample these rocks away from these thrust zones where the salinic deformation and metamorphism was minimal. And my colleague in Germany, Arne Wilner, did pseudo-sections and thermal calculations on the assemblages. And you can see is that the upper plate rocks, represented by the Bayford Oceanic Tract, were buried to great depths, 7.2 kilobars at temperatures of about 320, typically for cold geotherms associated with subduction zones to varying degrees. So again, that is not what you would expect in a soft collision and what you see in the Bay of Islands ophiolite and in the Quebec ophiolites. So the Notre Dame Arc and associated ophiolites basically indicate a hard collision, whereas the rocks on the west side of the Cabot Fault indicate a soft collision. So these two were not next to each other when they collided. So where was the Notre Dame Arc? So and on the slides on the left, you can see how I visualize how this process takes place. Basically, over time, the subduction channel is widening into the hanging wall and progressively picking up arc material and bringing it down, and then causing it to be metamorphosed. So this is a reconstruction of the Laurentian landmass prior to the opening of the Atlantic Ocean. It is a reconstruction from two of my colleagues at the GSC, they're now retired or gone, Jacob Verhoef and Walter Roost. And they did a very careful reconstruction and de-stretching areas which had undergone lots of stretching. And I superimposed the promontories re-entrance by Bill Thomas onto it. And I, with some freedom, I basically extended those promontories re-entrance all the way in between the Caledonites and the Appalachians. If you use the evidence for significant Devonian textural motions, based published, and all the evidence of how you do that by John Waldron and co-workers a few years ago, then you'll see is that whole area of Dashwoods, Notre Dame subzone, plus its associated Bayford margin, was sitting to the north of Newfoundland. And if you add all the evidence we have for Ordovician textural motion along that fault zone, and that's based on the work I did with Shufa Lin and students, you could imagine is that Dashwoods and associated part of the Laurentian margin were situated somewhere in between the Caledonites and the Appalachians. And one clue is the age of the collision. All the evidence in Dashwoods suggests that the collision started sometime between 488 and 480 million years, both on metamorphic zircons and contamination of arc plutons by Laurentian material. Whereas the collision at the latitude of Newfoundland started about 10 million years later, at 470 or even slightly younger, and even younger in the Quebec reentrant. So that's another argument, is that the two were not together. And the closest place where you find ages of collision like this are in the west of Ireland, in the Grampians, in South Connemara, which in many ways looks very similar to what you see in Connemara, because the rocks here are also, the upper plate rocks are also strongly deformed and metamorphosed. So to conclude, the Appalachians is an accretionary origin, lots of terrain were accreted, but only 2 were hard. Most were soft. The tectonic shows both soft segments as well as hard segments, which must have been juxtaposed by significant strike slip motion. And the one element that may have controlled the degree of hard collision is the syn collision magmatism, both during the Akkadian as well as the tectonic in places. It may have weakened the upper plate and may have made it easier to deform. Basically, that's it. Thank you.